Problem number 6 says that the proportion of individuals in a certain city earning more than $35,000 per year is 0.25. Okay, we need a notation for this, so let's try to summarize this. Let's say that the probability or the proportion of people making $35,000 a year or more, how about just like 35 plus, more than 35, that's equal to 0.25. And then the people having a college degree, so let's say the percentage of people having a college degree, how about C for college? This is equal to 0.10. And then we're told that suppose a person is randomly chosen and he turns out to be earning more than $35,000. And the problem goes on to tell us that the proportion of individuals earning more than $35,000 and having a college degree. Let's write that down. Here's a notation. Got to make something up. What's the probability of making $35,000 plus and, intersection, having a college degree? How about C for college degree? So this is the probability of making $35,000 or more and also having a college degree. And we're told that that number is 0.10. And now we're told that a randomly selected person turns out to be earning more than 35. So you know what? That's given. This is something that's given to us. So if there's some information, we're given that this randomly selected person makes 35 plus. And now we're asked for what is the probability that this randomly given person who makes more than 35,000 has a college degree. So what we're going to note here is that we want the proportion or the probability of a person having a college degree given that this person makes more than $35,000 a year. So we have a formula for this. Formula goes like this. In the top, the numerator, we're going to intersect these two events. So this is going to be the probability of having a college degree and making 35 plus. And in the denominator, it's always the event that follows the given sign. That's the probability of what's given. And in this case, it's the probability of being 35 plus. And we just happen to have these numbers. The numerator is the intersection of these two events, and that's 0.10. So we're going to get 0.10 divided by the probability of 35 plus, which is 0.25. This is the same as 10 over 25, which is the same as 0.4. Problem number 7 says that we've got a medical screening program that administers 3 independent tests. Of the persons taking the tests, 80% pass test 1. So let's get some notation for that so we can summarize that information. The probability of passing test 1 is 0.80. And the probability of passing test 2 says it's 0.75. And the probability of passing test 3, that's down to 0.60. And what we want to know is a particular participant is chosen, and we want to know what is the probability that he or she will pass all 3 tests. I'm going to write that like this. I'm going to write in English first. What's the probability that this person will pass all 3 tests? Now, writing in English gives me a little bit of time to think about what I want to do. And now I want to think about how can I get this in terms of these? Well, I'm thinking of it this way. To pass all 3 tests, what we need to do is to pass test 1 and test 2 and test 3. Now, as you can see, I'm writing everything out because it gives me a chance to let this evolve instead of just trying to jump to a number. It's common to want to jump to a number, but I'm going to try not to do that. What I want to do is just start with what I'm asked, how do I get there, and then write all of what I want in terms of the information that I'm given. Now, we are told that these events are independent. So when I have an and, I ask myself, are these events independent? And the answer here is yes, and I know that just because the problem says so. So this probability we're going to get by multiplying. So it's going to be the probability of passing test 1 times the probability of passing test 2 times the probability of passing test 3. Now, I know in this one you might be able to just go from this information right down to these numbers that we're going to write here, but then all you're getting is some information and a result. You're not getting any proof of the result. So if somebody was to read this, how would they know to get from all this information down to this information? But by writing what we've written here, what we're looking for and how we get there, the result is proven. So what we're going to get is the probability of passing test 1, that's 0.80, times the probability of passing test 2, 0.75, times the probability of passing test 3, that's 0.60, and then we'll multiply these numbers together, and when I do that, I get 0.36. In problem number 8, we're told that in a stereo system, 50 transistors, okay, so let's get this down. So N is equal to 50, and the probability of failing in the first 100,000 hours is 0.0005, which means tenths, hundredths, thousandths, 10,000ths. We would expect about 5 transistors out of every 10,000 to fail. And now we're told that to assume that failures of various transistors are independent of one another, and what is the probability that no transistor will fail? All right, let's get some notation for that. What is the probability that we get no failures in the first 100,000 hours? That's what we're looking for. So as we've done some other problems, I'm going to try to get this in terms of individual transistors. So I want no failures in terms of the individuals. So to get no failures, what we're going to have out of these 50 transistors is maybe, here's a develop a notation. I want no failure on the first transistor, and no failure on the second transistor, and ... and no failure on the 50th transistor. Now, we're given that the probability of a failure is 0.0005, so we could say that the probability of no failure is 1 minus 0.0005, which is 0.9995. Now, because the transistors are independent, we can multiply these together. Probability of no failure on transistor 1 times the probability of no failure on transistor 2, ... times the probability of no failure on transistor 50. So we're going to get 0.9995, 1, 2, 3, 4, 5, up to 50 times. So we're going to write this to the 50th power. And when I multiplied that out, although this is a perfectly good answer, I think, I got 0.9753. In problem number 9, we're told that a TV set contains 5 circuit boards of type A. So let's write that down. We've got 5 type A boards. We've got 5 type B boards and 3 type C boards. And then we're told that the probability that a type A board fails is 0.01. So we need some notation for that. So why don't we write something like this? What's the probability of a failure given type A board? I'll just put the type as a subscript. And that is going to be 0.01. And then the probability of a failure for a type B board, I'll subscript that. That's a 0.02. And the probability of a failure for a type C board is 0.025. Then we're told that failures are independent. And what we want to get here is the probability of no failures. So what I want to do is I want to get this no failures in terms of these individuals up here. So we want none of these to fail, none of the type A's to fail, none of the B's to fail, none of the C's to fail. Now, we know that the probability of a failure for a type A board is 0.01, so the probability that type A does not fail, that must be 1 minus 0.01, or 0.99. And the probability that a B fails is 0.02. So the probability that a B type does not fail is going to be 0.98. And the probability that a C does not fail, that's going to be 0.975. Now we want no failures. So how do we get no failures? That means I want no failure on the type A's, and no fails on the type B's, and no fails on the type C's. Now, I see ands here, and we're told that these events are independent, so I'm going to multiply these. Now, we've got 5 of these, right? There's 5 boards, right? 5 type A boards, and the probability that each one does not fail is 0.99. So we're going to have a multiplication of that 0.99, 5 times appearing as a factor. So 0.99, that'll appear 5 times. So how about 99 to the 5th? And then we're going to have 5 of these type B's, right? There's 5 type B's, and the probability that a B doesn't fail is 0.98. So we're going to have 5 of those 0.98s. And then finally, we've got 3 of these type C's, and we want 3 of those 0.975s. So we're going to have 3 of those 0.975 3 times, so we'll write that to the 3rd power. And when I multiply these out, I got 0.7967 when I round it to 4 decimal places. Now in problem number 10, we're told that a certain brand of long life bulb has a probability of burning out. Let's write something down here. Probability of B, say burning out in the first 1,000 hours, is 0.01. Then it goes on to say, suppose that we wish to light a corridor with a number of independent bulbs in such a way that at least one remains lit. Let's write something down here. Let's say the probability of at least one remains lit. Right, now what we're told is that that has to be greater than or equal to point, and then there's 5 nines here. We want that probability to be greater than 0.99999. Now this problem seems a little backwards because typically we're asked what is the probability of this event, and we're trying to find this number. Now in this case we're given the probability and we want to go backwards and actually find something about this event. So here is that business of at least again. So when I see that at least, we should start thinking the opposite. So let's think opposite here. And the opposite of at least one, right? At least one means 1, 2, 3, 4, 5, or so on. The opposite of that is none. So what we want to write is, now it's the opposite. So it's going to be 1 minus the probability that none stay lit. That's what we want. We want that to be greater than 0.99999. Now, the probability that none of them stay lit, all right, none of them stay lit, we could write that like this. 1 minus the probability that they all burn out. So the probability that the first one burns out, and the second one burns out, and the third one burns out, and ... and the nth one burns out. And we want that to be greater than or equal to point, those 5 nines. Now, let's do what we can to solve this. Let's subtract this 1 right here. And if we subtract that 1, we're going to get the probability that the first one burns out and ... and the last one burns out. That's going to be greater than or equal to, now, 0.59 minus 1 turns out to be negative 0.4 zeros and a 1. But of course, we're still going to have this negative sign right from here. So now what we're going to do is we're going to divide both sides by this negative 1. And we know that when you multiply or divide an inequality by a negative, that this symbol changes direction. So we're going to have the probability that the first one burns out, and that the second one burns out, and ... and that the nth one burns out. This is now less than or equal to point 1, 2, 3, 4 zeros and a 1. And because these events are independent, this is the probability that the first one burns out times the probability that the second one burns out times ... times the probability that the nth one burns out. And this is all less than or equal to 0.1, 2, 3, 4 zeros and a 1. And each probability of burning out, right, that takes us back up to the beginning. The probability of burning out turns out to be 0.01, and we have one of them, two of them, ... n of those. So we have n of these, and that is going to be less than or equal to 0.0001. So what we're trying to do is find a number n, such that when we raise 0.01 to that power, we get a number less than 0.001. And we're going to do this just by making some guesses. So if n is equal to 2, we're going to get 0.01 squared. And 0.01 squared, this is equal to there's 3 zeros and a 1, so we're much closer here. But less than or equal to 0.4 zeros and a 1? Nope, not quite, so that's still false. So we need to keep going. So let's try n equals 3. So this will give us 0.01 to the third power. And 0.01 to the third power, this is going to be we're going to get 1, 2, 3, 4, 5 zeros and a 1, less than or equal to 0.4 zeros and a 1. True. So we finally got a true statement here at n equals 3. So let's just conclude by saying we need let's say at least 3 light bulbs to make that probability less than 0.59.